Welcome to this explainer. Today, we're taking a deep dive into the absolute lowest, most powerful, and honestly most dangerous level of the entire Linux kernel. We are stripping away all those friendly interfaces to look straight at the raw machinery running underneath. I mean, think about it for a second. Do you really think your mouse, keyboard, or that blazing fast SSD just magically works the instant you plug it in? We expect instant results, right? But the truth is, the Linux operating system actually has no idea how to use physical hardware out of the box. There's an entire hidden world bridging that gap, and that's exactly what we're going to explore today. So, here's our roadmap for today. We're going to cover the hardware translators, controlling physical hardware, the illusion of local files, maximum power and danger, and finally wrap up with modern drivers and eBPF. All right, let's jump right into part one, the hardware translators, bridging the communication gap. The stark reality here is that the Linux kernel itself, it has absolutely no clue how an SSD actually reads data or how a GPU renders a frame. Why? Because every single hardware vendor out there, Intel, AMD, NVIDIA, Broadcom, they build their silicon completely differently. They literally speak different proprietary languages. Linux needs a way to understand them all. So enter the driver. You can basically think of it as a highly specialized translator. These aren't usually hard-coded right into the kernel forever. Instead, they're loaded on the fly as kernel modules. You've probably seen those .ko files, right? Like e1000e.ko for Intel network cards. And the really clever part is that when you plug in a device, the kernel checks its hardware IDs, like the vendor and device ID, say 8086.110FB. It uses those exact hex numbers to find and load the precise translator that piece of hardware needs. Now, if you look at how this architecture is layered, you've got your nice, safe user space floating up top, dropping system calls down through the network and file stacks. But right down at the very bottom, sitting at the absolute threshold between software and raw physical hardware, that's where the drivers live. They are the ultimate gatekeepers. Moving on to part two, controlling the physical hardware, direct access to silicon. Here's the thing. Drivers don't just ask the hardware nicely to do things. They completely control it using memory-mapped I/O, or MMIO. This is pretty fascinating. The hardware actually maps its physical control registers directly to specific hexadecimal memory addresses, like 0FUBF0000. So from the driver's perspective, controlling a physical chip looks exactly like writing data to a very specific magic location in memory. It all boils down to basic C programming commands. A driver can execute a simple function, like write lil, passing in a value and a register address. But, and this is crucial, this isn't standard RAM we're talking about. Writing a bit to that specific register might instantly spin up a network card, shoot out a packet, or completely reset the device. We are talking raw, direct access to the silicon here. Let's walk through a day in the life of a network packet just to see this machinery in motion. When a packet hits your network card, the NIC uses Direct Memory Access, or DMA, to write that data directly into RAM. This completely bypasses the CPU to keep things lightning fast. But, the CPU still needs to know the data arrived. Now, the NIC isn't going to sit there while the CPU constantly pulls it asking, hey, got data? That's way too slow. Instead, the NIC fires off an IRQ, an interrupt request. This literally pauses whatever the CPU is doing right then and forces it to jump to the driver's interrupt handler. The driver then checks its receive ring buffer, which is basically a high-speed waiting line, finds the packet, and passes it up the Linux network stack. All of this high-speed choreography is entirely managed by the driver. All right, part three, the illusion of local files, character devices in user space. So Linux intentionally hides all of this absolute chaos, the memory mapping, the CPU interrupts, from us in user space. It sets up these brilliant illusions called character devices. You've definitely seen them, /dev/null, the classic digital black hole, or /dev/random. From user space, they look exactly like normal, boring local files. You can read them, write to them, but they aren't standard files at all. They're actually direct interfaces backed by kernel drivers. When your application issues a standard C read command on a file like /dev/random, the kernel steps in and intercepts it. It looks up the file descriptor, finds the inode, and locates a specific struct called file_operations. Look at the .read, .write, and .ioctl mappings here. This table is literally mapping your innocent read request directly to the driver's internal functions. So what feels like just reading a file to you is actually triggering code execution deep inside the kernel space. Which brings us to part 4, maximum power and danger, operating without a safety net. The difference between these two environments is night and day. Up in user space, your apps are running in a happy, secure sandbox. You've got memory isolation. If a Python script or your web browser crashes, no big deal. The OS kills the process, cleans up the RAM, and you move on. But down in kernel space, you are operating on the edge of a cliff. There's no sandbox, there's absolutely zero memory isolation. To put it bluntly, a no-pointer or a buffer overflow in kernel space crashes the whole kernel directly. It's an instant kernel panic. If a driver developer makes a single tiny mistake, just one bad memory address, one overflowed buffer, it doesn't just crash the driver, it completely bypasses all system protections and brings down the entire operating system instantly. The dreaded kernel panic. And that ultimate, unrestricted power, that's exactly why drivers are the absolute holy grail for hackers. If an attacker manages to compromise or load a malicious driver, they literally own the machine. Hackers love to hide rootkits inside kernel modules because from down there, they can intercept system calls, secretly monitor network traffic before the firewall even knows it exists, or natively log every single keystroke. It is the absolute ultimate vantage point. Let's look at part 5, modern drivers and eBPF, observability in the core. First off, we have to realize that modern drivers aren't just simple mouse controllers anymore. High-end enterprise hardware like NVMe drives, GPUs, and SmartNICs, they demand insane complexity. Today's drivers handle multi-core queues, complex NUMA optimizations, zero-copy packet transfers, you name it. A modern high-end NICs driver can easily contain hundreds of thousands of lines of code. They're practically mini operating systems running right inside the kernel. So how do you monitor these incredibly complex mini OSs without accidentally triggering one of those catastrophic kernel panics? Well, the Linux community gave us eBPF. This is an absolutely revolutionary observability tool. eBPF lets engineers dynamically and, most importantly, safely insert monitoring hooks right into driver events. It's kind of like having a shielded magnifying glass directly on the silicon. You can monitor packet flows, block I/O, or IRQ latency in real time, right at the driver layer, without risking a system crash. It has totally changed the game for how we observe the core. Ultimately, this really is the true core of the system. Every single packet of data you download, every file you read from disk, every tiny movement of your mouse, it all fundamentally relies on a Linux driver working flawlessly in the background. They are the essential physical bridge connecting the digital Linux kernel to the real world. If you found this descent into kernel space even half as fascinating as I do, you're going to want to stick around. Be sure to subscribe, because in future explainers, we're going even deeper. We'll be unpacking the intricate architecture of Linux DMA, how PCI drivers communicate, and exactly how NVMe achieves those blistering storage speeds. I'll leave you with this final thought. Now that you've seen what's really happening beneath the surface, are you content staying comfortably up in the safe sandbox of user space programming? Or are you ready to step over the threshold, embrace the danger, and master the raw power of the kernel driver? Thanks for joining me on this explainer, and I'll see you in the core next time.